Welcome to this talk session. So first of all, a quick reminder. The talk is like 15 minutes, including questions. And I hope for those who are online, everything works. And feel free to ask questions in the chat. So I think we can start with Alberto, and so it's yours.
Hello, everybody. Thank you for staying to the last day. I will try to keep on time and be reasonably interesting, hopefully. This is work that is now being... Other microphone? Yes. Okay. So this is work currently being done in Prague, but in cooperation also with people in Munich and elsewhere. And it relates to a kind of spectroscopy that we actually didn't hear about here, but belongs to what can be done very nicely with this family of multiple scattering codes. In particular, this is spectroscopy that involves measurements of some inelastic processes, namely measurements of Magnus dispersions, which are here depicted as a cartoon in one of the experimental methods that you can use to probe such kind of excitations. Essentially, a magnon is a deviation from the magnetic ground state of magnetic material, which has a collective nature and involves, in particular, the precession of local magnetic moments, which you can measure, for instance. Well, classically, you would use neutron scattering. If you have a thin film, it's more convenient in some cases to use spin-polarized electron energy loss spectroscopy. You can do resonant inelastic X-ray spectroscopy. You can do spin-polarized STM. There are a variety of techniques, each with strengths and deficiencies. But now, the point is such properties of the material are intrinsically governed by the geometry and the composition of the material. And for functionalization, you want to control these properties. That's the common thread in all kinds of fields. This brief talk is about one possible idea of how to control such kind of physics. And it's basically a bone thrown to experimentalists if somebody would ever want to try it. The idea is that basically, as I said, a magnon is a precessing deviation from ground state of the local magnetic moment. And the question that this work tries to address is whether you can try and manipulate it and predict from first principle how it should look like if you excite this mode under an external electric field. You could control this physics by temperature, you could control this physics by applying a magnetic field, but an electric field in a configuration that looks like a MOSFET is probably the most convenient you can think about for a variety of reasons that time doesn't allow to go into. So this is the cartoon on the left of the device. On the right, it's a tentative experimental realization of this device where you could imagine about doing a Fabry-Perot spectroscopy, essentially, interferometry between part of the sample that is subjected to an electric field and part that is not. Again, time is a bit short, so I will jump ahead. If this works, it doesn't. Sorry. It's okay. So this is the goal. Now, as I said, this is not experimental work, it's theoretical work or numerical work. How to compute such properties, and in particular to compute them in this scenario where they are supposed to be probed out of equilibrium and not infinitesimally close to equilibrium condition. This is a kind of physics that people study in linear response at the most advanced level, I would say. But linear response doesn't cover necessarily the regime where you want to have a finite electric field applied. So you have to think about how to do it. And okay, this is one slide to summarize a lot about linear response, but some people here are much better expert than me. The idea in linear response is that you would use basically Kohn-Sham susceptibility and Gross-Kohn theorem to compute the independent particle response function, and then dress it up with the exchange correlation TDDFT kernel that captures the part of the physics that you want. And for magnons, transverse magnons would essentially be related with the deviation of the direction of a magnetic moment in the plane that is orthogonal to the globally collinear ground state along Z. So it's some circular motion of the local magnetic moment. And you can capture it by introducing, for instance, circular coordinates. And then it's just a block of the linear response tensor that you have to study. But we had also heard here, it was last week, Julie and other people spoke about this formula. They may have used a slightly different notation. This is copied and pasted from the original literature. Essentially, multiple scattering gives you this scattering path operator, and it is built from the local solution. I can show that with this formula that is basically an implementation of the Lloyd formula and basically goes back to Hein and the local force formula. It's the same building blocks, for instance, for magnetocrystalline isotropy and for other effects. You can use multiple scattering to obtain directly an estimate of the deviation of energy from the ground state when you have a magnetic moment on atom I and on atom J, and you tilt them both by a certain quantity. And this is the building block for the Heisenberg problem. And once you have the Heisenberg problem, you can basically simplify a lot the kind of work that you would have to do in linear response. And you get essentially the same physics, but with some crucial differences. And the difference is that linear response gives you the full susceptibility, collective excitation and single site excitation, or single particle excitation, sorry. When you use the root of computing exchange parameters for the Heisenberg-Hamiltonian, and then you solve the secular equation of the Heisenberg-Hamiltonian, basically you look for eigenmodes, very similarly to what you would do for phonons when you study the dynamical matrix. And I have a cartoon about that in a second. You get the dispersion as a function of Q vector. The matrix that you diagonalize is Hermitian. The dispersion is eigenvalue, it's a real number. You get this part of the formula. This part of the formula would give you the spectral function of the magnon with some broadening that is artificial, just numerical escamotage to avoid divergences in the denominator. What the linear response gives you as an improvement is a better position of the poles in terms of position in the real axis, and also, let's say, the broadening, how much that excitation would leave at that particular Q vector. And this you would lose if you do only calculation of exchange parameters. And now the question is, can we estimate this part of the formula cheaply? And can we use this technique to actually evaluate the expression under additional influence of an external electric field? So to do that, as I said, the basic building block was to use Liechtenstein formula or magnetic force formula, as whatever you want to call it, to estimate the Heisenberg exchange parameters. This is just a formulation of the standard secular equation problem applied to magnons rather than phonons, but it's the same kind of physics. These are lattice Fourier transformation of the Jijs, and you check for which omega of q you have a solution. And then you can think, what is actually happening in the linear response when you do, in particular, this random phase approximation, and you get just chi0. And there are works from the 80s, the 90s by Yoshida, and people keep rediscovering this old literature over and over and over, that basically associate the dominant, not the only one, but the dominant mechanism that produce damping of Magnus or broadening of what is measured in these spectroscopies with the so-called Stoner excitation, that are basically independent particle spin flips that involve a certain conservation of energy and momentum. And okay, you can come to that in different ways, but that's it. As I said, you could compare this one by one with phonons. The physics is the same to some extent. Main difference is in the masses that for phonons, of course, come from the ions. For Magnus, you don't really speak about masses, but you speak about an excitation that lives in the same space as electrons. Other fundamental difference is the order of the differential equation involved. For Magnus, it's a precession. It comes from a torque formula. Essentially, it's a first order differential equation. For phonons, you would have second order. It's not so crucial. The point is, you get a dispersion from the eigenvalue of the secular equation, and you get the ability of recognize how much that excitation involves a certain sublattice of the system from the eigenstates of that diagonalization. Now, again, we go back to multiple scattering. Multiple scattering is very nice because it gives you this localized splitting of the problem into the problem around each atom, each sublattice in your unit cell, or each atom in your cluster. And what I was saying a moment ago is that in order to find to estimate the damping, in order to estimate how long an excitation, a collective excitation can live, one way to think about it is what else can compete, what else could happen at that Q vector. And if you believe this experimental theoretical literature, the main thing that could damp a magnon or basically give a finite broadening is this other kind of spectrum, the Stoner spectrum, that is spin flips between basically occupied up electrons to unoccupied down electrons, conserving energy and making sure that you take into consideration occupation, so that's the theta. And then you have to think about where this competition happens. So it has to happen at the same Q vector, And if you have more than a single sublattice or you have more than a single magnetic layer, you have to identify again where it comes from, but you have it from the Heisenberg problem. That's in the eigenstates of the Heisenberg problem. The eigenvalues give you the omega of Q, and the eigenvectors give you sublattice projected how much that excitation was involving one spin or the other. Okay, now second part, electric field. How do we put a finite electric field for the kind of problems that we want to consider? This week a little bit, we heard about non-equilibrium Green function theory. That's extremely powerful, also complicated. We don't need it here. Here, the point of view is that we want to study a problem that you can approach from the electrostatic point of view. You have a substrate, metallic, non-magnetic. You deposit a finite thin film of magnetic material, and then you have a certain dielectric barrier. Here it could be just vacuum. And if you think about it, you can basically simulate the effect of an applied electric field by putting an auxiliary layer, artificial auxiliary layer of charges that in the limit of being dense enough and far enough from the sample surface will behave like a metallic slab producing a constant electric field. And this technique has been used in DFT level multiple times. It was used in Dresden, and Hongbin Zhang used it for his PhD thesis to do magnetocrystalline isotropy as a function of electric field. It has been used in Halle by Stepanuk, Ignatiev, and in Jülich as well. And we have used it a little bit recently in Munich, and we hope to continue a bit more. Main thing is that this technique allows to describe electric field, but with a barrier. If you want to do ohmic situation where the electric field can produce a steady state current, then you have to go to some level of Cavendish Green function formalism. That's not touched here. Here, we only want a constant field across a dielectric barrier. And now we start to have the results, and hope so time is running out. So we have a technique, we have a goal, and we have to think about a minimal system that can display the effects that we want. And we start simple, slab, thin film, monolayer of iron suspended in vacuum. Density of states and Magnus spectrum. And you see basically nothing, because the electric field acts orthogonally to the thin film, but the polarization of the monolayer of iron at this level shows almost nothing. If you look very carefully, these three lines that correspond to three different values of the electric field, 0 would be equilibrium state, black, red, and blue are out of equilibrium, but steady, no transient. It's there, but it's nothing to even think about. And in the DOS, you see nothing. But we know what to hunt for. The point is, here we see nothing, because the electric field breaks the symmetry along Z, but everything translates rigidly as an effect of electric field. We modify the mapping tin 0, but the Fermi level follows, and that's why we don't see any practical effects. But we know then that if we have something else that breaks the symmetry at the beginning, like the substrate, then we have a reference to which the electric field can couple and will manifest its effects. And this you can think to push, maybe this I will skip. If you select your materials carefully, Hubert mentioned the case of iron impurity in palladium to give a magnified magnetic moment as a result of easily susceptible palladium acquiring spin polarization. You can follow that thread of thinking, and you can think that iron, rhodium, or some auxiliary alloys would be very good candidate. This is about very simple cases, just iron on top of copper, 001, monolayer. These pictures are pictures of the Bloch spectral function of the electrons, where red and blue are the spin up and spin down states, taken at the Fermi level. So these are slices of the Fermi surface of the 2D Brillouin zone, because it's a 2D periodic system. This is without perturbation up and down, and energy a little bit above Fermi level, a little bit below. And here you start seeing that since there is a substrate that already broke the translational invariance along Z and made it asymmetric plus Z minus Z, once you further change the situation with the electric field, you modify the hybridization between iron, let's say, and copper in this example. And this transfer of spectral weight is the basic ingredient that enters the Liechtenstein formula and the calculation of the damping. So, okay, this I will skip, but very quickly, these were a slice, the 2D Brillouin zone and the Fermi surface across it. This is more standard representation of the Bloch spectral function, so path across high symmetry points and energy, blue and red spin polarization, and some broadening because you have a termination, so it's not periodic in the orthogonal direction. And you see spectral weight changing with the electric field. Okay, so now the results for Magnus. And first of all, for DOS. And to remind you, this is the system. Substrate, one monolayer of iron. And you see how the DOS shifts a little bit as a function of the perturbation. And
Alberto,
yes?
I think you have to conclude now.
Okay, thank you. I think I will jump. Just say it works. Okay. It's perfect. No, it has its limits. And just a bit of the focus. No conclusions, those to speak of. Maybe one thing, okay, it works in both levels. You can change the lifetime. And you can change, if you have a more complex structure, you have as many Magnus modes as magnetic sublattices. And you can change properties like the gap, the distance between acoustic and optical modes. But sorry, it was too much.
Okay, so thank you, Alberto. Sadly, we don't have enough time for questions, but feel free to ask him during the break. So now I think we can start with the next speaker. The mic is here. Okay, change. I mean, there's a poster.
This is the forward.
Yeah.
Progress.
Okay, so good morning, everyone. So my name is Jia Wei. I come from the Czech Academy of Science. And first of all, I would like to thank the organizer for having me give a short presentation. So my topic today is about a single impurity Anderson model out of equilibrium. We use a two-particle semi-analytic approach to study this problem. No? Okay. So the outline is that I will first give some background in introduction, and then our reduced packet theory, and then give some result, and finally is the conclusion. So the model we study is actually very simple. It is just this. Sorry. It is this quantum dot coupled to two magnetic needs. And this quantum dot, it has some on-site Coulomb repulsion, so it generally is a many-body problem. And if there is no applied external bias voltage, and then the left chemical potential and the right chemical potential, they are the same. And this is the typical, the Anderson impurity model. And now we can apply some biases across this system, which drive the system out of equilibrium. So in general, we just use the non-equilibrium Green's function method to study this problem. And here is the Hamiltonian of this system. I think most of you are very familiar with this. The model is simple, and so the physics is not that quite simple. So in general, first you can imagine that if the quantum dot is completely decoupled from the needs, so what will happen? The single particle spectral function is just contains two peaks. One is at the minus u half and another at the plus u half. And if now you turn on some weak interactions between the quantum dot and the needs, you can expect that the single particle spectral function looks like, the single particle spectral function looks like this way. It has some small smearing around this u half. And this is true, but this is only true when the temperature is larger than the Kondo temperature. Here is the Tk. But when the temperature is smaller than the Kondo temperature, the physics behind it is that there is another so-called Kondo peak develops at the Fermi level, and the width of this Kondo peak is actually logarithmically scaling with the increasing of the on-site Coulomb repulsion U. So our theory is just to capture the physics behind this model. So far there are actually many kind of methods to study this impurity model. For example, like the NRG, the numerical renormalization group, which seems to be the widely used method and also serve as the benchmark to this impurity model. And the next is somehow like the tensor network. I think later Gabriela, she will give an introduction on this tensor network method for this impurity model. And the other methods such as like the quantum Monte Carlo, the equation of motion method, and the many-body perturbation theory method. But one thing I want to stress is that none of this method is applicable in all situations, and the new approach is always to say develop for this enduring problem. And our method is actually based on the many-body perturbation theory. So, I first in this slide I will give to discuss the problems in the standard many-body perturbation theory. So we can see in this figure that this is the x-axis is the on-site U, and the y-axis is the magnetization. And this result is calculated by the Hartree fork. And you can see that when you increase the on-site interaction, the Hartree fork, predict some magnetic order when the U is larger than some critical values. But you know that due to the Kondo effects, to say the system should be always in the non-magnetic phase, which means that the Hartree fork, it predicts a spurious phase transition in this model. The reason that caused the phase transition is that in the standard many-body perturbation theory, it has an ill-defined critical point because the Swinger-Dyson equation and the Ward identity, they cannot be simultaneously held. So our approach is just from that the two-particle vertex. We define only one vertex and then do the self-consistent on the two-particle level and to calculate this system. Okay, so I will give some introduction about our theory, the Parquet equation. So this is generally the three-channel Parquet equation. The Parquet equation actually is nothing but the classification of the Feynman diagrams on the two-particle level. So if you look at the two-particle, the Fourier two-particle vertex here, it can be generally divided into two parts. The irreducible part and the reducible part. Because there are, to say the two-particle vertex, it has four external indexes. So you can, in general, have three ways to split these diagrams into two parts by cutting two Green function lines. So in principle, you can define the three channels. Here is the electron hole horizontal channel, the electron hole vertical channel, and the electron hole and the electron channel here. And also due to the fact that the reducible diagram in one channel is irreducible in the other channels, so we can also write down the Parquet equations, which somehow mix these three channels. And in principle, if we can self-consistently solve these diagrams on two-particle level, and then we can get the two-particle vertex, and then you can know the self-energy. So, but our reduced Parquet equation actually works only on the electron hole channel and the electron channel. The reason is that we find that the third channel share the same critical fluctuations as the previous two channels. And here I give the Feynman diagram of our reduced Parquet equations. In principle, by solving these two equations self-consistently, you can get the two-particle vertex on the two-particle level. And this is the corresponding equations of this Feynman diagram. And the one thing you should be stressed here is that these two particle vertex, they actually depend on 4 time indexes, which is extremely computational cost. So we also do some further approximations on this reduced packet equation. We call it the local time approximation, which means that we approximate these non-local two particle vertex with some local vertices. And after this simplification, we can write down our reduced packet equation to a very simple way. It's here. And here is the renormalization integral. The explicit formula is written down here. And so far, we know how to calculate these two particle vertices. And once we know these vertices, then we can we can calculate the self-energy. Because I have mentioned that the Swinger-Dyson equation and the water identity cannot be simultaneously held. So in practice, we divide the self-energy into the even sector and the order sector. The even sector is calculated by the Swinger-Dyson equation, and the order sector is determined by the water identity. Okay, so far all these formulas they are formulated in the chaotic space. In practical implementation, you also need to use the Lagrange rules to analytical continue from the chaotic space to the real-time domain. So far, I have finished introducing the theory. Then I will discuss some results. The first thing is that our theory can be analytically solved in the Condor regime, which means that the U is very large in this region. The main result is that we reproduced this logarithmic Condor scaling. The main result is here. The coefficient is 1/4. But the exact solution from the best ansatz is the pi/8. So we don't claim that our theory is exact, but at least we can analytically reproduce the Condor scaling of this system. So in general, the theory should be solved numerically. And here I point out the IV characteristics in the Coulomb blockade regime. So the parameter I choose here is like the U equals 40 gamma, and the corresponding Condor temperature is very small. And so the system, the temperature I used is like the 0.1. It's much bigger than the Condor temperature. So the system is in the Coulomb blockade regime. So as I mentioned before that the Hartree fork and the GW method, they can predict some spurious phase transition. So here you can see it clearly that when the voltage is not very large, and then for the Hartree fork, the blue curve, and the GW, I think, is the orange curve. And they both have, they have two solutions. One is magnetic and another is non-magnetic. But the magnetic solution is completely wrong because the physics is not in that way. And our packet equation here, the red line, we only have one solution, which is non-magnetic. And the stability of this solution is guaranteed by the magnetic susceptibility, which I plotted in the subset. So at the beginning, which you can imagine is that when you turn on, when apply the voltage at the beginning, because the U is very large, so the transport is largely blockaded by the on-site Coulomb repulsion. So the conductivity, the conductance is very small. And when the voltage just is compared to the U, and then the electrons can just overcome this Coulomb blockade, the Coulomb barrier, and then the conductance increased in this region. And also, we calculated the transport at the linear response regime. So when the T is very small, here the T is smaller than the Condor temperature. Here the Condor temperature is 0.1, somehow like this. And when the T is smaller than the TK, the system is in the Condor regime. The Condor regime means that there is a central Condor resonance peak at the Fermi level, which largely enhances the conductivity in this regime. And when you increase the temperature, when the temperature is larger than TK, and then the Condor peak, the Condor peak is destroyed, and then the conductance rapidly decreased. And we are now in the Coulomb blockade region. And when you further increase the temperature, and then the systems was driven into the sequential tunneling region. Finally, the conductance will drop to 0. And also, we calculate the, far from equilibrium, this case. And we can see that here the temperature is 0, and I turn on the applied bias voltage. And you can see that when the bias is very small, and here is the system is in the condor region, and when you turn on the bias, the systems go into the Coulomb blockade region. The spectral function behaves quite similar as the temperature. But one thing I should mention is that the bias voltage, to say, instead, the bias voltage can destroy this condor peak, but additionally, there are some local peaks around each chemical potential develops here. But these potentials will be finally vanished when you further increase this, to say the applied bias. Okay, so this is our conclusion. Our reduced packet equation completely suppresses the spurious transition, and the logarithmic condor scale is analytically reproduced. And okay, let me finish my conclusion here. And the three transport and we reproduce the three transport regime in the linear response. And also the bias plays a similar role as the temperature, but it develops some local peaks around each chemical potential. So that's all. Thank you.
Okay, not working.
Yeah.
So thank you very much. Maybe we have time for one question. Yeah.
Okay. So you showed you compared your new theory with the well-known Hartree-Fock and others. So I'm not familiar, but you showed in the Hartree-Fock solution here, you have two solutions for low voltage, and is the lower one, the dotted one, is a non-magnetic, right? The dot, you have two blue lines, so the dotted one is a non-magnetic solution. Okay, so I guess that the magnetic is the stable one in this regime. Yeah. Yeah. So if you look at that, so it means if you choose among the two solutions, the right one, the stable one, then you have here dotted line, and then later on you have only one solution, which is also correct. So roughly speaking, even the Hartree-Fock behavior is not totally wrong, right? I mean, you're
if this is a stable solution, and this is also the stable
yeah.
The problem is that there is a phase transition.
Yeah, okay.
But you know that the Condor problem, it is not a phase transition, but a crossover.
Yeah, okay. Thank you. Just to clarify. Okay, thank you.
Okay, so sadly we don't have enough time for other questions. We can applaud him again. And now the next speaker. Oh yeah, and please turn off your phone if it's possible. Yeah, I will.
Where's W? Jesus, why is this a check keyboard? But that's okay. Wait, where's the dot? What the f? Oh, sorry. Yeah. Almost done. Wait. What the? Okay. Wait. Aha.
It's the computer from the school's computer.
Ah, I see. Please be right. I can't type it again. Ah, okay. Thank God. Great. So, wonderful. Right. I did not realize that I was audible before this, but that's okay. Okay. So, yeah. So I'm just going to get started because I took some time to type it in. But don't worry, it's a very short presentation because I really want to have more questions and all of that. So yeah, this is me. If you don't know me, then, well, I get paid by these guys, these guys, these guys. I'm here, and these are the slide licenses. Okay, if you're interested in the presentation, the slides themselves are hosted on GitHub. You can check them later, and also they will be on an own cloud somewhere. You can also interrupt me if any part is unclear. It's a short one, though, so yeah. Okay, so very quickly, programming languages. So because I got this question a few times, why do we have languages? Why does it matter? Blah, blah. And then I was reminded of this fantastic quote, which is, there's no such thing as a machine-independent program. This was a very popular point of view back in 1980. Okay, and the reason is simply because of automated coding, or as we now more commonly call it, compilation, or compilers, basically, and standards. So how does it work, and what exactly does it mean when we have a programming language? Well, it is essentially the layer between you and your machine. There is also the little known linker and loader part, which is fantastically complicated to work with and a lot of fun if you're interested. But mostly people focus on first link, which is that you have code, you have a compiler, and then it spits out some sort of assembly. You compile it, becomes an executable, and you execute it. Technically, it becomes relocatable machine code because it needs to be fitted into the memory space of your operating system, all of that, which is fun but not very important for us yet. It will become important because when you want to transfer different programming libraries from one part to another, then you actually need to care about that last bit, because who else is going to handle it? It's just going to be the operating system and the calls which are done within the operating system between these two libraries. And now, a very common thing is, this is a compiled program, but nowadays we have interpreters, which is great, but that's not really how they work. So they have implementations, like Python is typically CPython or JPython, etc. And those are actually compiled. So they do the same thing. It's just that at runtime, they allocate a lot more memory. It's sort of like they have a third layer. It's like a virtual machine, and you use that. So yeah, that's here. And what is the problem then? We have standards, and this is a little joke thing which we discussed over the school with some people, which is that what does it mean if you have this character 10, blah 8, or character star 8, blah 1, what does it mean? What's going on out here? And it also debunks a very popular myth, which is that Fortran 77 is 100% BAT compatible with Fortran 90, because the sad reality is it's not true, because on the right, you have an example of what is from I think it was the 1983 ANSI Fortran Information Handbook, which very clearly tells you that the first line is supposed to be, it's definitely allowed. It has a length specification of 8, and it's a character array. Sadly, from Fortran 90 onwards, this is technically undefined, because anything with character is supposed to become length or kind, and no one writes kind for character. It's almost always A unless you're writing a different language. Don't do that. So yeah, there's a problem out here, right? And this is why we have standards, and it's a lot of fun to talk about new languages, to say, oh, but Julia doesn't have this problem, or Rust doesn't have this problem, because then there's a different problem there. You can't even point to one standard, because it's whatever you downloaded off the internet the day you did it. Great. And then there's Python, which has this amazing problem that if you call this, then it resolves to a different path. And this is fun because it's a fun example, what is going to be executed? Or is this going to error or not? It's a lot of fun. Oh my. I don't know if it's that short, but maybe I can try to speed through the beginning. Sure. Yeah, you can just share this one, I think. Or is that the full screen? Yeah, that's the full screen. That's better. Yeah, awesome. Okay. for the benefit of those who are there, don't worry, we didn't do much. I will see if I can very quickly go back. Yeah, this is useless. Okay, right. So the story here is that back in the day, you couldn't port codes from one machine to another, and the reason is essentially this last part, that once you've compiled your code, it needs to load and run on different machines, and this is difficult because they all have different memory, etc., layouts, Cool. And the way to protect yourself from all of these things is to have a language standard, because then it becomes someone else's problem, really. And that problem becomes, the compiler developer's problem. How do I ensure that it runs everywhere, because otherwise people will complain and call you an idiot? And yeah, so this is more about what I was saying on the last slide, that, this is the nice Fortran 2021 standard, well, 2020X, and this is the nice old Fortran 77 standard, which was so much simpler because, clearly they didn't have any of these many issues, which is great, but they needed it, so they put it in, and so now it's everyone's problem. The slide is not really meant to be read. The only thing to see here is that back then you were allowed to declare an array right here, whereas nowadays you're not. That has been silently dropped out of this entire thing. Arrays can only be declared on the other side once you've already defined a variable. Okay, coming to something actually which I did, which was fun. So how do you write a compiler anyway, and what is a compiler written in? Well, I was working on this project, Fortran, with some fantastic people there in the acknowledgements. I'll get to that. And it's actually not that bad in terms of lines of code. It's barely 50,000 lines of code. I'm sure we've all written 50,000 lines of code once in our lifetime, right? And the funny thing is, if you talk to anyone who does a lot of C, then the actual fun part is, by the end, the best way to write C++ and C, first you write your own, then you write objects, then you write templates, and then you write a Python program which copies all of that and changes variables in it, because there's too much even still. So that's about generated code. The representation here matters though. So we already talked about how one layer of representation freed you from this I can't run my code on a different machine problem, which is when we all forgot about linkers and loaders. No one thinks about them very much now. Similarly, compilers too nowadays are not just, okay, I got your code, I parsed it into a token tree, I was just looking at every single line, etc. That's not really what happens. Well, it does happen. That's the abstract syntax tree. But there's another layer which we did for Fortran, and that was really the key part. It's the abstract semantic representation. There's an example right at the end, but the point is, the abstract syntax tree is a direct representation of your code, okay? And you can catch certain errors there, for sure. If you start a variable with a number, sure, you can catch that at this stage because that's illegal. Great. But some other subtle things, like if you pass the wrong kind, for example, or if you pass a kind which doesn't exist, these are things which you can't tell just by parsing because you need a lot more information. At the very least, you need to know all the modules that are being used. You need a structure, right? And which is why, for example, Fortran actually defines things by the module and not by the header and source file of C, C++, etc. The abstract semantic representation is therefore a simplification from the abstract syntax tree, but it's not machine code. It is instead the simplest possible way to check against a standard. So anything which reaches the ASR stage is guaranteed to be correct Fortran, correct by the standards, which is great when you're writing a new compiler because actually writing the backends are the real problem. So if you have something which is already correct Fortran 100%, then you can very simply write a backend in Python, backend in C, and eventually, yes, you need to write for machine code. So we write LLVM, which is another intermediate layer between you and the machine code. So this is obviously the fastest and the most, it is the fastest one, but it's also the most difficult to write. But since we have this middle representation, which gives you all the information you need, you can very quickly write the Python or the C++ backends. Okay, so these are some of the features. Once again, it's mostly, there was another interesting thing which happened here, and that is when you think about something like sine or cosine or something like that, then typically, if you look around, then most of the time people will tell you to just call a hardware function, something from hardware or something from libc, because why not? Everyone has libc. And that's, if you think, conceptually, that's not pure, because that's not an implementation in Fortran. And it's very popular. It's popular from the days of GCC, which I'll show at the end why. But the essential idea was everywhere you ran Fortran, you already had C, so why not? That was the idea. And So this time what we also thought of doing is that let's have a pure Fortran version. Because if you have something which is pure Fortran, sure, it might be a little slower on certain hardware, sure. But it's also guaranteed to last longer. Think LAPAC or BLAS. These things last because they're old and because they never changed and because they are hardware independent, And yeah, these are some features. Yes, it also has an interactive thing, but this is a little bit of a weird feature because when you have interactivity, this means that, okay, if you've seen a large program which made a lot of modules, then it typically makes a lot of small module files. Not so with Fortran, where if you want to run it on Jupyter or something, you need to have the full information, which means your module files get bigger and bigger and bigger and bigger. Has its pros and cons. It's great for a teaching tool or just for a demo, but not so great in production. But then who runs interactive in production anyway? Okay, so now another, and the last fun part really, before I wrap up, is very simple. We all probably have taken numerical methods in some form or another, that you have all these matrix problems and you have stability, numerical stability, etc., etc. Sometimes you will see people trying to converge things down to machine epsilon, which is this number here. It is the smallest representable number. It's actually pretty damn small, so you actually don't see this in practice. What you do see in practice are magic numbers. Now, and this is what the rest of this is about. It's about what sort of magic numbers can you be allowed to use. It's great if you have a magic number like 1e minus 5, 1e minus 2, no problem. You're never going to run into a problem. But if you go down, if you go to 1e minus 16, 1e minus 30, so-called chemical spectroscopic accuracy depending on your units, you might have problems. And if you're wondering right now, I don't care because I write my own libraries and I write my own algorithms and I know exactly what's going on. Well, there's another thought coming. And this is going to be the example. It's an elementary function. I have actually done a trick here because it's not important to talk about that one. So you need to fold the initial argument down to minus 2 pi to pi to 2 pi, which I've already done. You'll call an IEEE function. I've not mentioned that here, the details, because it's not important for this. What is important is here, where we're saying that, okay, if I have sign between 2 pi and minus 2 pi, then I can fold it. And I'll actually go through these graphically, but it's very simple if you look at this. In fact, let's just do that. Why even talk? So we say that, okay, it's symmetric, so you can fold it around there, and then you can take the absolute value. Then the second time, you take the minimum. Then you repeat it on the right, and then finally, see you have that little tail there. You chop it off with another minimum. Okay, great. And what happens then? Okay, cool. So I've chopped it up, now, damn. Yeah, now what? So then for that region between minus 2 pi and 2 pi, you can actually do, well, typically you can fit a Chebyshev polynomial, you don't want to really do a Taylor expansion, they converge very slowly. But the most popular ones are the min-max polynomials. And for that, now you have two options. You can do it yourself, where again you have this convergence problem, how much convergence do I have, and you're back to that whole machine epsilon problem which you're trying to solve. Or you can do a nicer thing. You can use one of these certifiable things which mathematicians use. They are effectively infinite precision, but you can set a precision if you want. Then you get very small number of coefficients, 8 in this case, because sine, as you know, is it's odd, right? So you can zero out the rest. And let's see how it works. These are the auxiliaries. You can see them in the slide. They're not very important to talk about, but they're just exactly what you'd expect. To implement modulus, then you also need floor, right? And to implement floor, you also need abs. There's literally no surprises right out here. Here's the problem. Okay, it's great. That's what we expected. It's 1e minus 16 over minus 2 pi to 2 pi. It is 1e minus 16 over minus 20 to 20. Fantastic. It's not so good as you get to a larger number. And it gets pretty shitty pretty fast, okay, beyond the point. And if you think about this, as I mentioned early on, I cheated in the beginning, and the range reduction to minus 2 pi to 2 pi is exact. Okay, let's not talk about that. So why is this happening? Well, because it's being called in a loop right over here. It's being called in this loop. This function is calling itself again and again and again. And this loop is doing this division in the modulo function. Now, by the way, these results were compiled using gfortran, which means I wasn't using this modulus function. I was using whatever gfortran gave me. And what does that tell you? It tells you that, well, if you want actual precision, you're going to have to go and either use higher precision. You know, you can fix this problem very simply. If you use quad precision, or then you get a slightly better one. If you use infinite precision, you don't have a problem. But it's extremely slow. You can't do that in practice. There are algorithms for this. For example, the cheat which I used is that there's a function defined in the IEEE standard, the remainder with pi over 2, which I used. But definitely, the takeaway from here is that don't just assume that because you have written something and it's standard, you're using the standards. The standards don't guarantee a precision which you might be looking for all the time. So that needs to be checked.
Sorry, I think you have to conclude now.
Oh, okay, very quickly then.
Yeah.
I'm almost done. Right, so here we have Fortran code. Then how do you call it in C? Well, if you remember from the library thing, what you can do is that you can define, the only problem is that the memory links need to be the same, that the sizes of the variables, all these things calls need to be the same. The standard way from 2003 onwards is to use the ISO-C binding. I worked with someone who's very fond of this. I am too. It's great. You can call Cython or CFFI if you're not interested in writing your own C code, and you get a nice Python module. If you can't do that or you don't want to do that, there's F2Py for people more like us, because if you don't want to keep up to date with all the standards, then you can use F2Py. I'm working on F2Py. It's going to support F90 very soon. The design is essentially it has a parser of sorts, and it's a best effort thing, and it allows you to call C. The reason behind that is because you want to do a callback as well. You know, as you saw, Sylvain has done that. And the good thing is it's not a compiler. Originally, I was very upset about that. But because it's not a compiler, you can do a lot of stuff. The bonus thing, which we don't have time for, is what the hell is this doing, and why can't I read it? Because we all do code.
Sorry, I think I have to stop because
okay.
yeah. Today, time goes fast.
This is the answer. But yeah. So document your code, and yeah, I don't know if we have any time for questions. Wow, that took longer than I expected. Sorry. Oh, yes, and this is my advisor. He's great, you know. Yeah, cool. Thank you.
Okay, so thank you very much. And so no question for this talk. And I think we can continue the session.
Put it in the slide mode. Okay, so I use this. Okay, so I'm Ryunosuke Sagehashi from Chiba University in Japan. So I'd like to present about my research. The title is Theoretical Analysis of Resonant Auger-electron diffraction patterns in ferromagnets. At first, I'd like to explain about resonant Auger-electron spectroscopy. It is a spectroscopy of resonant Auger electrons. These electrons is generated by a resonant excitation process like this. It is an example of M23M45 process. In this case, at first, an electron at L3 level excited to M45 level by incident light, and it is a resonant excitation. And there is a core hole state at L3 level. So to fill this state, an electron at M23 level drops to this hole, and energy generated by this dropping. And by this energy, electron at M45 level emitted to vacuum as a resonant object electron. Finally, there is 2 electron for state, and it is final state. In this process, there is a absorption process. So it is possible to obtain information of valence band elements by using resonant object electron spectroscopy of alloys, chemical compounds, of layered structures, and so on. In previous study, measurement of resonant object electron diffraction pattern of magnetized nickel were conducted. The experimental geometry is like this. In this experiment, nickel was magnetized in plane direction. As a result, these patterns were obtained. This left pattern shows left pattern is the resonant object electron diffraction pattern of nickel 111 surface. It reflects the surface structure of nickel 111 surface. And right side shows the asymmetry of these patterns. Difference between the patterns obtained by right circular polarized light and left circular polarized light. In this asymmetry pattern, there was a strong decoherence, and it could not be explained as a diamond effect. That is, the diffraction effect occurred the difference of emission angle of electrons. And this angle difference, this shift is obeyed this equation. Also this decoherence has had a relationship with the magnetization of nickel. So these results indicate that the possibility of measurement of a magnetic state by using a resonant object electron spectroscopy. So we conducted the calculation with this model to analyze these results. Next is calculation procedure in this research. The intensity of resonant object electron is obey this equation. That is called Kramers-Heisenberg formula. In this research, first we calculated object electron source wave function with atomic multiple model. After that, we using these results, we conducted the scattering calculation by using EDAC code. That is a software for multiple scattering calculation. And then we made a theoretical asymmetry of a resonant object electron diffraction pattern. And in this calculation, we use this geometry. This geometry is same as experimental geometry. And this cluster was composed of about 300 nickel atoms. Next, that is results. First, we conducted the calculation of vertical incidence to the surface. Therefore, we obtained this pattern. This asymmetry pattern. Comparing with experimental pattern, this pattern shows difference decohesions. In the case of X-ray magnetic circular dicohesions, the intensity is obeyed this equation. So if the magnetization and incident light is vertical, the intensity of XMCD became 0. So in this pattern, it shows also no magnetic circular dicohesions. And next, we conducted the calculation with 55 degrees incidence, like experimental geometry. Therefore, these patterns were obtained. Left side shows the patterns of resonant Auger electrons, and right side shows the patterns of photoelectrons. Photoelectrons shows different no MCD, but however, on the other hand, resonant Auger, the patterns of resonant Auger electrons shows clear dicohesions, like experimental pattern. So these results indicate the absorption, the MCD is the absorption process is necessary for MCD. In the case of photoelectrons, it is direct process, so there is no absorption process. So in this case, downspin electron and upspin one can excited respectively. However, in the case of a resonant process, it includes absorption process. So in this case, only downspin electron can be excited. Additionally, we also conducted the calculation per LS multiple term. That is energy levels per spin large S and orbital angular momentum large L. It's split by spin orbital coupling. In the case of this nickel, 8 electrons at 3D orbital, there are 5 multiple terms. So we conducted the calculation per these 5 terms. Therefore, we obtained these patterns. These patterns are zero-time scattering. So we obtained these patterns without EDAC code. These patterns shows a clear circuit dicohesions at all times. However, in these patterns of one-time scattering, it shows a difference. Circuit dicohesions respectively. Especially P3 terms shows so weak magnetic circuit dicohesions. The reason is the diffraction effect is stronger than is the strongest among of them. And we also confirmed the effect of scattering. In EDAC code, one-time scattering include the zero-time scattering. So we subtracted the intensity of zero-time scattering from one-time scattering. Therefore, these patterns shows no magnetic circular dicohesions at all times. And we also conducted the same calculation at not magnetized nickel, and comparing with the pattern of only scattering. Therefore, there is no difference. So no difference. So the difference. So a diffraction effect is not is independent on magnetic cycle. Independent of magnetization of nickel. This diffraction effect is diamond effect. Diamond effect is not affected by magnetic state of sample from these results. Finally, that is conclusion. In this research, it was succeeded to reproduce magnetic cycle dichoisms on resonant Auger-electron diffraction patterns of magnetized nickel 1-1 surface by calculation, and magnetic cycle dichoisms on resonant Auger-electron diffraction patterns depends on the direction of magnetization and the vector of incidence. And diamond effect is independent on magnetization. Also, resonant Auger-electrons shows dichoisms like X-ray magnetic cycle dichoisms. That is all. Thank you for your attention.
Fine, thank you very much. So I think we have 2 minutes for questions. No one? I have to. Okay.
What exactly is diamond effect? Okay, sorry. That is diamond effect is the phenomenon of a difference of emission angle of electrons, photoelectrons. Due to circular polarization of incident light. Yes.
So it's a geometry-related effect.
Yes. Yes. So and this angle, difference angle, obeyed this formula. Yes.
So the theta there is the incidence or the emission of the photoelectron.
Yes.
Okay, thank you. Everyone? No? Okay, so I think I will close this talk. Thank you very much.
Thank you.
So the next speaker, please. It's Gabriel.
Can I try this one? If it plugs and doesn't work, then I don't try it. It was this folder, the presentation.
Recording stopped.
Okay, so where is your presentation?
On the folder that opened there,
This one?
yes, there is
I
a
see.
yes.
Okay. So let me just put up in the. So this one?
Yeah. Yeah, it's better to share the whole screen and then we don't have to change.
Okay, so that is this one, I think.
Yes, the con. Yes.
Okay, so
Yes. I think F11 it might be there.
let me just recording.
Recording in progress.
Okay, so we should have the
Full presentation. Okay, yes. Let's see if this works. Okay, it works. Yeah, okay. So, well, I'll tell about this. Good morning, everyone. So, for those who don't know, my name is Gabriel Rodrigues. I'm working in Stockholm University. I'm originally from Brazil, and that's why here in the background of this cover, I put this. This is like a church in my hometown, and it looks like a spectrum. So I thought it was nice to use. Okay, it could be XPS spectrum, XAS maybe. It will be more suitable. Okay, so I'll talk in a more chemical. I have a more chemical presentation. Of course, chemistry is physics, so there's physics in there as well. And I try to keep it simple. So let's go. Okay, so what I'll try to have like a general approach of what we do, or especially what I do in Stockholm University in the Oh yes, sorry. What I do in the X-Solas group in Stockholm University. So it's the X-ray science of liquids and surface. So I work in the surface part, and we have a problem. Put here. Hello. Okay, looks fine. So we have an environmental problem now. That's especially it's really on the news now, especially because of the last IPCC reports on climate change. So this is actually a BP statistical review of British Petroleum of like energy use from 2019 2020. So I tried to cap before the pandemic. So we can see that we actually, although our best efforts and the use of renewable sources has been increasing, we're still using more coal and we're emitting more CO2. So this is a big problem. And of course, I don't think like science alone we will solve everything, but we are scientists, so we try to help in the best way we can. One of the main process in industry in general, and in the chemical industry that can help in this, it can be catalysis. So we work with catalysis. So I don't think everyone here knows this, but usually, especially for industrial applications, a chemical reaction most of the time has like a high activation barrier, and for a bunch of purposes. So what we want is to actually decrease or to have a new pathway that will not go through this high transition state or activation barrier, and this is catalysis. So we will introduce something that will not participate directly on the reaction, in the sense that it will be renewed, and it will make our reaction faster. But of course, sometimes we have like transition states or energy barriers which are lower and accessible at the thermic level, but we can have like a much more complicated reaction path. And then we have to understand, especially if you want to do catalysts that are even more efficient and it can work on good work conditions. So we work with heterogeneous catalysis, which is thus that the reactants are in a different phase than the catalyst. So we work with solid catalyst, and usually our reactions work in the gas phase. So this is what we want. And one of a good method. So before this is two of the reactions that we studied there. They are quite studied reactions already. They have like a lot of things in the literature, and they are used already in the industrial applications. So this is an example. So the Fischer-Tropsch reaction, which we have syngas, which is like a carbon monoxide, and hydrogen gas, and we try to convert this in the other more value chemicals like ethanol, methanol, and higher carbon fuels. So this is more or less the path, or like a general reaction path for this for this reaction. So we absorb CO and H2, and they dissociate, and you start to grow your carbon chain until you have like several products. And this reaction usually it's done in like higher pressures, like 10 atm, and usually above 200 degrees. And this is the Haber-Bosch that maybe it's more known because it was like a fundamental discovery of humanity, especially because with Haber-Bosch reaction, we produce ammonia, and with ammonia we produce fertilizers that are, of course, everyone knows how important a fertilizer for the food production. And this is also done in like 10 to atms, and also higher temperatures. So it would be nice if we find catalysts that are even good enough that we don't have to work in such higher conditions. And in order to do that, we try to understand better this reaction, especially one of the tools that we can do for this is X-ray photon electron spectroscopy. So so far we haven't used any like a multiple scattering approach to our studies. So the thing I have used more to compute X-ray photon electron spectroscopy, or XPS, it's a simple yet efficient delta Conshan or delta SCF approach. So we have our initial state, which is just like the ground state level. And then, of course, there's been many discussion about this here. We emit an electron, and then we have our final state. And in this delta SCF or delta Conshan approach, our binding energy, which is the energy that our electron is binded to the core, it's just the energy of the final state, the ionized state, and the initial state, which is the ground state. And so this technique, it's very selective because the core binding energies are very well defined. It's quantitative and has a good detection limit experimentally. Okay, so this is a new equipment that was developed in our group. It has been started some years ago, and now we are having like the first results, and they will be starting to be published soon. So the difference here is because usually the experiments were done in like high vacuum chamber, and with this new equipment Polaris, the experiments are done in high vacuum chamber, but we have this new approach here, which the gas is injected quite close to where the reaction in the surface. So we have a local, a small part that has this high pressure, like a local high pressure, and we can study this reaction at the atmospheric regime, for example. Okay, so going back to computing binding energy. So it's important to have, especially like when you have these experiments, a lot of times they are very difficult to interpret, or you don't have reference, so the theory can help in this. So in this delta SCF approach, like I said, we compute the energy of the ground state, we compute the energy of the core hole state, and here it's very important, like here, for example, when we're dealing with metallic surface, the experiments are grounded. So when an electron is removed from the core, a charge screen comes from the metallic surface and screen this electron. So usually goes to the Fermi level, and this effect is really important in your computation. It makes all the difference. And the binding energy will be the difference of this final and the initial state. And usually we don't compute absolute binding energy, especially with DFT, which each functional you will have a different absolute energy. But usually the errors are systematic, so you compute chemical shifts, which is just the binding energy difference of different species. Like here, for example, if you have a molecule and on a surface in two different sites, A and B, we have only one initial state, also in experiment, which is like the molecules absorbed there, and you have two final states, which is the core hole when in the molecule in the site B, and the core hole in the molecule in the site A. So our chemical shift will be the difference between these two binding energies. So this approach is nice because you have we have like some core, we have some relaxing, usually like atomic relaxant at the core level, and you have relaxing in our valence band. And here's example. These are experimental spectra for Fischer traps on cobalt. And for this one, we got some nice results. And how we could use this, for example. So here, sometimes it's difficult, especially you have these broad bands, and we don't know what's going on there because you can have a lot of different molecules that are absorbed. So if you have a theoretical spectra, for example, shifting accordingly, we can see, for example, that in the start, in the small temperatures, we have this kind of more CO. It's like CO adsorbed on many different adsorption sites. But then, as the temperature increases, we start to produce the CH products, or even like C2A2. So our carbon chain grows a little bit. And also here is like the oxygen spectra that start to shift, like to produce some water or something. Okay, so and then so this delta SCF usually works nicely, but I want to show another aspect that I think is very interesting. It's also a way to understand how this core level effect, and it's the core effective or the Z+1 approximation. So it's an intuitive way to understand. So if we have our atom, then we light X-ray, for example, and we have a core ionization or a core excitation. Because the core levels are like very localized, and also the core hole, usually you can say that you remove the point charge, or you can approximate this effect as a removal of a point charge in the case of an electron from the core. Or we can also say that we add a positive point charge at our nucleus. So the carbon, for example, would be, with a core hole, will be chemically equivalent to nitrogen, of course, without the core hole, and with one less electron. And this approximation is intuitive and usually works really well, especially for checking, because the core hole calculation can be more complex, especially if you have some effects like exchange effects in the core and valence and etc. So here, and it's also experimentally shown that it works. So here, for example, this is an experiment. We have N2 on the nickel 100 surface, and the binding energy difference between N1 and N2, it's 1.3 eV. So because it binds in this vertical way, the nitrogen that is binding to the surface has a different binding energy than the nitrogen on the top. So if we think about the Z+1 approximation, if nitrogen it's ionized, then we can think that it's going to be it's going to behave chemically as the next element in the periodic table, which is oxygen. So this will be equivalent to ionizing the nitrogen on the bottom and here on the top. And here, experimentally, if we compute the difference in absorption energy of nitrogen binding these two different ways, we get exactly the same results, which shows that the Z+1 approximation, yes, seems reasonable. Seems a good guess for this first approximation. It will not always work, but usually it gives like good trends and is a good initial start to understand your problem. So here we have some calculated results. So this is like experimental. This is like a CO on nickel as well. So we can see that this is RPBE, and we usually have good agreement between the binding energy chemical shifts between experiment and the calculation. On parentheses, we have the Z+1 calculations. So usually they are quite close. For carbon here, they are not so close to the one using core hole. We justify it. We think we haven't investigated this deeply, but we think it's because there is a difference between the singlet and the triplet state for carbon in these two cases, and our calculation just take like the average. So this might be, or maybe some exchange effects.
Yeah, you run out of time, so.
Okay, so yeah, I just wanted to show, like here, for example, we could get that we were getting shifts not so close to the experimental values, and with the Z+1 approximation, we we saw that it was closer to 0.3, which is the experimental value, and then we could guess that maybe there was some problem in our calculation. So these conclusions, I said something already about the Z+1 approximation. Just want to show like our group, a bit old picture, but yeah. And thank you very much.
Thank you very much, Gabriel.
Yes.
So no questions, unfortunately. Okay, so yeah, but we don't have enough time, so maybe during the break. We take one? Okay, okay. Yeah, and it's still one speaker left before the break.
15 minutes late.
Yeah, but I think during the break it will be nice to ask questions. Okay, next speaker, please.
You have 5 minutes, Peter. Well, I start with the conclusions. Yes, that's it. You can close that.
The first calculations that I showed. Oh, wait. You'll have to talk to everyone right now again. Yes. Thank you very much.
Can you hear me this way? Nice, maybe you can. Okay, hello everybody. I try to be quick. So I would like to speak about the scaling properties of response functions, especially the polarizability, the dipole polarizability, and maybe later about arbitrary response function. I mean here the system size dependence of response function. So everybody knows this, textbooks physics, we have some molecule, we put in an electric field, inducing a dipole, and the polarizability measures how easy to distort our electric field or electronic cloud. In quantum physics, we can calculate the polarizability through the second-order perturbation theory, and we shouldn't forget about this sum over states has a continuum part, and even for hydrogen atom, the 20% of the polarizability comes from this continuum dipole transitions. So what is the physical picture between this, beyond this dipole polarizability? So we have a ground state, we have a dipole transition, and the system is excited, and it goes back through a dipole transition to the ground state. So we can see this picture as a fluctuating dipole. The dipole polarizability is really important everywhere in spectroscopy, every kind of field of chemistry and physics where we have electric field. It's really important to calculate intermolecular interaction, parameterize force fields, calculating van der Waals interactions, and also to defining new generation of DFT functionals. So how to calculate this response function? Okay, we have this sum over states. Of course, nobody wants to use it. We have external electric field. This is the most popular way to do it in quantum chemistry, but it's really expensive. Of course, we can use the Green's function. In chemistry, it's not so popular, but this tool is really great, so I have a new idea here. So we can calculate the first-order wave function, solving the inhomogeneous Schrödinger equation. Really nice, beautiful, but there is a rule of thumb. The bigger the system size, the bigger the polarizability is. It is a well-known rule. So it means there exists some kind of length scale that connects the polarizability to some kind of system size. And I would like to find this system size dependence of polarizability. Check the textbooks, open a really modern one, or even Jackson's electrodynamics book. We have a conducting sphere with a radius r, put in an electric field, and we calculate the displacement of the electric cloud. And between according to the force balance, we can conclude that the polarizability is proportional to the volume. Really nice. Everybody using in the literature, more 100, more 1,000 publication, relying on this classical scaling law, many force fields, van der Waals corrections. So, but this is a classical result. What is happening if we want to find the quantum mechanical scaling law? We need to somehow measure the system size in quantum physics. The volume is not the best way, because we have arbitrary dimensional systems sometimes. We need to define a norm to measure some length scale. And what is the best norm? The L2 norm. Why? Because all of the directions are separated, and of course it has a really nice meaning. This measures the uncertainty of the position, the fluctuation of the position, and this is only a ground state property as the system size. Okay, calculate the polarizability using this length scale. We have some systems. We can solve analytically the problem, calculate analytical polarizability. And here comes the nice thing. We found the same formula in every case. Here, the mass of the system, the charge of the system, and here the uncertainty of the position to the power of force. And this property is pure ground state property. And we have a constant factor in every system. And this constant factor for the ground state is pretty close to 1 in every case. And those systems are quite different spectrum. Here we have only bound state, bound to bound transition. Here we have only bound to continuum transition in direct delta. Here for the hydrogen atom and the square well, we have both bound to bound and bound to continuum transition. And we find the same formula for the different symmetry. And also for excited states, we have the same formula. So something strange is going on here. Test or method, test or new formula. For example, calculating molecular polarizabilities using this Tkachenko-Scheffer method, what is a really popular method to calculate van der Waals interactions. And the first step of this method to decompose our molecular polarizabilities into atomic polarizabilities. But here, these are the effective atoms, not the free atoms. They are dressed up by the molecular environment. And we're using this scaling law to define the polarizability, this effective polarizability, through the volume of the free atom and the effective atoms in molecule. And we can calculate this effective volume through the partitioning of the electronic density somehow, for example, Hirschfeld partitioning. And we can calculate molecular polarizabilities. Nice, nice, but we have a small systematic error, 8% around. Try to use the new scaling law. It's beautiful. It disappeared. Technically zero, the systematic error. So the concept works. Okay, what is the picture? Here we had excited state fluctuations in the original picture. Here we have pure vacuum fluctuations. Something is strange because this part contains only ground state properties. What about C? Maybe C contains the excited state contribution. Okay, so far I discussed only the dipole polarizability. Oh, I have 8 minutes, nice. So we have a general formula based on the uncertainty or the vacuum or the fluctuation of the given state. It can be also an excited state, not necessary to be a ground state. So it measures the uncertainty or the fluctuation of the position of the dipole. And we have a nice formula. And the C factor is pretty close to 1 for ground state polarizabilities. And here comes, what is the meaning of the C? Is it possible to derive this formula? Or what is about other response functions? And what is about frequency dependence? Okay, go further and do some derivation. Here is in a really short way the multiple polarizability. I omit here the frequency dependence, but it is also possible to use frequency dependence and derive everything, including frequency dependence. Here we have the multiple transition matrix elements, but in principle, it can be arbitrary operator. If you want, it can be the correlation energy, if I'm using here the correlation operator. It can be arbitrary response function. Here, I'm using only position-dependent functions. For example, a multiple operator. If we are lucky, we can rewrite, without derivation because it's long, we can rewrite in an exact way a response function where we have still the transitions, multiple transition elements, and we have a new factor here in the denominator. It is still a ground state property. It contains the gradient of this multiple or the response operator. For the dipole operator, this is 1. If we are lucky, we can give an alternative form of this guy. And here appears the fluctuation of our operator. It's pure ground state property. And everything else here is an excited state property. And this guy here is a dimensionless factor. With further modification, we can show the second part is also proportional to L4, and the C factor is nothing else as an average excitation energy. So we somehow renormalized and put every excited state property in the C factor and separate it from the ground state fluctuations. So a further analysis. This term and this term, if you consider in ground state, both term is positive, always positive. It means when we consider C equal 1, it means we have equal energy level for the excited state spectrum. This is the well-known Untitled approximation. And in this case, the polarizability or the response function is a lower bound, strictly lower bound. And the meaning of this C factor, as I mentioned, is some kind of averaged excited state contribution to the quantum fluctuations. OK, some further analysis. I have time. We have two different forms of this formula, containing the ground state fluctuation or containing the excited state picture. Stay here for this excited state picture. We can define in this bracket this guy as a fluctuation matrix. If I put together these two terms, these are the diagonal of diagonal terms. What is the meaning? It still shows some kind of fluctuation picture, but in this case we have two joint fluctuation. And how to calculate the response function? We summing up over the elements of this matrix, of course. But we realize, I cannot prove yet, but this matrix is diagonally dominant according to some numerical experiment for the ground state. It means the diagonal elements are much bigger than the off-diagonal elements. What can we do? Approximate with the trace of the matrix. If we diagonalize the matrix, it's invariant. The trace is invariant, so we can use the eigenstate. Some further notification. F is positive definite. For the ground state, each term is positive. In this case, we can use the Perron-Frobenius theorem. Each positive definite matrix has largest eigenvalue, what is positive, and there is a huge spectral gap after this eigenvalue. So we can approximate this trace with the largest eigenvalue. And it seems to be the largest eigenvalue is the ground state fluctuation. So we renormalized and we separated the ground state fluctuations from the excited state fluctuations this way. So we replace this picture, this joint fluctuation, with the vacuum fluctuations. So as a summary, we have a universal scaling law. It contains only ground state properties here, and every excited state property is renormalized in the C factor. Everything is rooted in quantum fluctuations. If I want, I also can derive the frequency-dependent form. This is just an approximation because I assumed here only a single resonance frequency, and the single resonance frequency can be calculated from the ground state property like here. And it's valid for almost everything. And maybe it opens a new way to parameterize force field, van der Waals interaction, or calculate correlation energy if somebody can figure it out how to calculate properly the C coefficients. Thank you very much.
OK, thank you, Peter, for this very interesting talk. We have time for some questions. No, not for the moment. Yeah, Peter?
Well, it's a very nice thing you discovered. This was not known that the quantum mechanical polarizability in the quantum mechanical theory you get a completely different scaling law. I mean L4 rather than L3. This was
no, it was not clear. No. Somebody, I show it. And somebody measured it for quantum dots recently. Measured the polarizability through terahertz spectroscopy. And they found this 4-dimensional scaling, but they concluded it's some kind of quantum confinement effect. If you have a confined system, a particle in a box, yes, you have. But this confinement radius is not general. You cannot use for a hydrogen, you cannot use for a harmonic oscillator to define the system size properly and in arbitrary dimension.
But then comes my follow-up question. So, of course, there's some quantum fluctuation,
yeah,
but
of course.
But what goes wrong? The most simple free electron confined sphere, which would be maybe closest to we can test, you know, the quantum. That's what we want to say, probably, no? If you, what makes this the change from the classical mechanics to the quantum mechanics? I don't know.
The interesting thing,
complicated.
nobody using it. There are hundreds and thousands of publications using the classical scaling law. And it changes the picture.
Thank you very much. Another one, maybe? No? Okay, so time for the break. Thank you, Peter.
Thank you very much.
Yeah, so now like 50